Hello and welcome back to another episode of Math with Son. Today we're going to be doing free body diagrams in AP Physics 1. So a free body diagram is used to make and represent what is happening with all of the forces. So right here we have a box, and this box is probably being pushed or pulled or something like that. Let's say that it is a box being pulled on the ground. All right, if the box is being pulled on the ground, the length of each of these vectors would indicate the force in which something is actually occurring. Okay, so if that is the case, if we were pulling this on the ground, let's say we were pulling it to the left. If we were pulling it to the left, that would be the force of the tension of some sort of rope or something like that. And what force is acting against the rope being pulled this way? If that box is on the ground, that would be the force of friction, opposing it. Remember Newton's third law that every action has an equal and opposite reaction, so the friction force is opposing it. Now notice the friction force is a little less than this tension force. That would indicate that this has a non-zero force sum, which means the box would actually move or accelerate to the left. Then the downward force would be called gravity, and the upward force is called the normal force. The force of which that everything that is on the ground is feeling and being exerted essentially by the earth. Okay? So that is those guys. We're going to do a quick vocab thing review, and then we're going to do an example of some situations of what is happening. All right, so gravity. The first force that we will investigate is gravity. Gravity is negative 9.8 meters per second squared. It didn't have the squared. The force is equal to the weight. The force of gravity, according to Newton's second law, would be mass times gravity, negative 9.8 meters per second squared. The normal force is the force of Earth that prevents you from falling into whatever. Okay, so typically it would be the ground, but it could also be a table or something that an object is sitting on. Okay, so that was why we drew our normal force facing up. There is the force of friction. There is pushing and or pulling an object. And there is tension. Tension is whenever you have like a rope or something like that, which is very similar to pushing or pulling. Okay? With that in mind, I wanted to do a quick little thing with the box as well in relationship to free body diagrams. So here, if we had a man trying to pull a box across a floor with a rope, identify the action-reaction pairs. So if the free body diagram was in frame of reference of the box, then the box would be pulled from the rope over here, and the friction that would be acting against it would be in this direction. But if we were referencing it to the idea of the man was essentially over here, and he would have the tension being pulling this direction and the friction would be opposing it. Okay? So it would flip depending on your frame of reference. All right, that being said, let's do an example of a book on a table. If you have a book on a table, that's the most boring example of a free body diagram that you could have because you got table, you got book. The only thing that is occurring on that would be, this is the dot for the book. You have the normal force, which you can call Fn or F normal. And you have gravity, which would be the same length because that book is not shooting through the table, or Fg. It is just staying there, one would think. Gravity. Okay. What about if that box or book is being pushed across the floor? Well, if that's the case, you would have the dot for the book. You would have the force of the push. Notice it's not being pulled. You would have the force of friction. Force of friction. You would have gravity, which I ran out of room for my vector, gravity. And you would have the normal force. And you could abbreviate all of these. You have Fn. We have force of push, force of gravity, force of friction. Okay? So you can abbreviate each and every single one of them. All right? Sliding down a hill. These problems are going to be the ones that get a lot of people. So we have a hill. we have the dot for our sled. The sled is going this way. The sled is moving to the left. Yes, 100%. Sled is moving to the left. But what is causing the sled to move to the left? Well, that would be gravity, and gravity is not moving to the left. Gravity is moving straight down every time. Gravity is always going to be moving straight down. What is keeping this sled adhered to the ground, which is a hill in this case, is the normal force. Well, the normal force is not straight up this time, because if it were straight up, that would not be keeping it necessarily perfectly on this hill. It is going to be always, always, always perpendicular to the surface in which you are dealing with. Friction will be always, always, always parallel to the surface you are dealing with. Force of friction. And it would be going in the opposite direction of which the object is traveling or pushed or what not. In this case, it's not being pushed. If it was being pushed, we would have another arrow down this way, but it's not. It's just sliding down the hill. Okay? An elevator. An elevator, we have a dot for the elevator. We have the tension, force of tension of the cables and strings and stuff like that cause the elevator to not plummet to the ground, and that is battling the force of gravity. Now, depending on how we wanted to go up or down or stationary, this guy where I got my vectors like equal, this would be stationary. Elevator's not moving. But if the force of tension is greater than that force of gravity, which way would we go? Well, if the force of tension is pulling us up more than gravity is pulling us down, we would go up. Versus if the force of tension was smaller than the force of gravity, then gravity would be winning the battle, and we would be going down in this elevator. Okay? So that's a simple explanation of how those vectors can indicate which direction you are actually moving, and how free body diagrams can, and you'll see very quickly how they can make problems that would have been relatively difficult a little bit more easy to understand. That's going to do it for this one. Until next time, everybody, I will see y'all later. Bye.